Sandeep, am I audible?
Yes, sir. Yes, sir.
Okay. I'm waiting for Dharmi to join so that we can start. Okay. Would any of you have a question? Any of you have a question? Morning, all of you. I don't know. Any questions? Any questions? Is the board visible?
Yes, sir.
Okay. So I'm going to try this new experiment. Let's see if it's successful. Now, let's start with your responses to my question. Tell me a few takeaways from yesterday's class. A few takeaways. You can either use your voice or on the chat box. Yesterday's takeaways. Resistance in series and parallel, okay. That was just start from the previous class. Elastic modulus, okay. So we understood E. How many of you are able to see what I'm writing? Any of you? Oh, you can see, right? Okay. Okay. The other one is strength. Strength in EMPA, stiffness in terms of GPA. Okay. Very good. What else? We replaced force with stress and strain. Very good. Very good. Higher modulus for stronger materials. Very good. Dependence of stress on cross-sectional area. Well, stress has to do with force per unit area. Yeah. So we usually use MPA here, GPA here. Elastic modulus, sigma, epsilon. What else? How about this? What did we do for this? Strain. Strain. We said we would use percentage. Very good. And then we also said apply slash it, and that is the deflection. Right? Anything else that we did? We looked at stress strain curve for different materials. So I'm going to start with that stress strain graphs for different materials, and then we will move on to the next. Okay. If you have a question, don't hesitate asking. All right. Okay. So let's move on. I'm going to erase this. Ask you a few questions. Okay. Ready? So I have strain here, stress here. This is in EMPA. For now, let's see. This is the curve that I'm getting on an experiment. This slope would be nothing but slope of is material property, which is E, right? Don't use any other word Y, I mean letter Y and all those. Just use one of them, which is what we are going to use all the time. Okay, this is E. All right. Now, let me plot a few curves. Okay. Supposing I have one curve like this, another curve like this, what do we understand? One curve like this, another curve. I did an experiment. The first is stiffer compared to the second, right? So let's use this and draw certain curves. Okay. And I'm just going to give you an idea of how we view it. Supposing I have one that goes like this and fails. Here it fails. And there is one more that goes like this and then fails. What's the difference between these two? First is brittle, correct? This is brittle and this is brittle, and that is, don't use plastic here. Don't use plastic, Janisha. Ductile, right? This is ductile. Okay. Now, there is this portion, let's say around this point and this point, which is proportional limit. Okay, so this we can call as proportional limit. Same with this is proportional limit. Okay, beyond that, what happens? It is no more in proportion. All right. What's the difference between proportional and elastic? Supposing I conduct an experiment, I get this kind of a curve. If I ask you the question, is it elastic? How do you know whether it is elastic or not? How do I know? We discussed this. I'm asking is how do I know if the response is elastic or not? How do I find out? Let's go back to that question. How did we define elastic? If it retraces the original path, the original configuration, very good. If there is no permanent deformation, then it is elastic. All right. So tell me which one of these curves is elastic. Very good. Okay. Tell me which one of these curves is elastic. We identified one to be brittle, the other is ductile. Fine. Both are elastic. How do we know? How do we know what should we do in order to? So supposing I do a test and I want to find out whether. So let me take one of those samples. Let me take usual guy, which is this. Okay. Let me take this. Now I'm conducting an experiment. Okay. I'm pulling this. I'm pulling this. As I pull it, I notice the variation of force with deflection appropriately divide by the original length and the area, and I get stress strain curve. Now tell me, is this elastic or not? What do I do? This is a very important thing that we need to understand. Even if I take a few more minutes. I conducted an experiment. I pulled it gradually so that I get these two graphs for two different materials. How do I know whether it is elastic or not? Proportionality must be there between epsilon and sigma. Yeah, so what you're saying is if it is proportional, it is elastic. There's one key point I made when I said elastic. What is the other word that I used? The material is elastic, or what's the other word that I used? starts with R, reversible. So if I do an experiment and get a curve, how do I know if it is elastic or not? Based on this word that I used. Go ahead, think. I, I'll repeat the experiment. I have this experiment. I pulled, and as I pulled, I measured the deflection and plotted this curve. It should retrace the same curve. What does it mean? I mean, what should I do in the experiment? What should I do in the experiment? One single word is the answer. What should I do in the experiment in order to find out whether it is elastic or not? Increase or decrease? Fantastic. So basically, I not increase because I increased only and got this. I need to do unloading. Unload. Understand this, right? I stretch, but that's not enough to find out whether it is elastic or not. I need to unload, and if I unload and it returns, say I loaded till this point, and if I unload, it went like this, then I know it is elastic. Proportional, let's say I have this curve. I'm going to use that curve again. This curve, let's say I did the experiment, I got this curve, I unloaded, I got this curve. This is straight, this is straight. Is this elastic? The answer is no. And therefore, don't confuse with proportional and elastic. The two are very different. So note that this limit that I have drawn over here, this limit that I have drawn over here is the proportional limit. And this is also proportional limit here, right? Sometimes the elasticity may be a little bit more than the proportional limit, okay? So this you can call as elastic limit, okay? In order to call this elastic limit, I should do loading and then unloading, loading, unloading to find out where exactly this starts to have permanent deformation. In a very similar way, here also, there could be a very small change for which it may be elastic. And what is this point? This point is point of, point of, what shall we call? Breaking or fracture, okay? And how about this? This is also a point of fracture. Okay. One more point to note. So if you have, let's say, we've gone to this point, and let's see whether it responds in a different way. It responded like this, which means that it had a permanent deformation. This means that this point at this point the material has reached. The material is at this point. The material is. I unloaded. Fantastic. It is inelastic. Okay. So we have a portion which is elastic. So this portion is elastic. So let me erase all this so that it's clear to you. So till this limit, it is elastic. Any other limit, so in this region that I have, the material is plastic. Okay. Or if I don't know whether it is plastic or not, I call it as inelastic. All right. Okay. Let's say I conducted the experiment. Listen to me very carefully. I'm going to erase this. So we looked at brittle, we looked at elastic limit, elastic limit, also proportional limit. We also looked at inelastic. Let's say I conducted an experiment. Once when I conducted the experiment, I got something like this. Another time I conducted the experiment, I got like this. Same material, same material. Is it possible? Again, let me ask the question again. I conducted two experiments on the same material, okay, identical, let us say. One experiment gave me this, so this is one. The other gave me this, which is two. Possible? Possible? Let's say temperature remains the same. Is there a possibility that I'll get two different curves for the same material? For the same material? Think, think, think. Let me give a clue to you. When the loads are different, no, see, load when I am increase the stress, it is nothing but loading, right? It is nothing but loading. I gave you a clue earlier, which is to do with this clay. This is a clay, correct? I'm doing an experiment. Just watch me carefully. So I'm doing an experiment and gradually pulling it. As I pull it, it becomes easy for me to pull. All right. So I conducted one experiment. Okay. The same material, same geometry, etc., etc. Now I conduct the experiment. I get something. All right. Again, I conduct the experiment. Just watch me carefully. Again, watch me carefully. Same material. What I'm doing is I am increasing the stress. I get the deformation. Force is increased. In both of them, force is increased. Here also I increase the force. Here also I increase the force. What's the difference? Time taken to increase. Fantastic. Yes, Shadvik. Time, what shall we call that as? The rate at which I apply the load. So supposing I get two curves like this, let's say this is for a rate. So which means, let's say I apply strain rate. Okay. So the strain rate, how do I represent strain rate? How do I represent strain rate? What shall I do? Epsilon, epsilon, epsilon. Yes, epsilon dot. So let's say this epsilon dot happens to be, let's say, 1% per second. And this happens to be epsilon dot is equal to 10% per second. Right? And it is possible for me to get two different curves. If it gives two different curves, what shall I call that material as? The material is what dependent? The material is what dependent? Rate dependent. So this is exhibited by rate dependent materials. Okay. So when I did this experiment, when I did this experiment on this clay, when I applied the load gradually, it deformed to a certain extent, but I did the same thing, but this time I threw it down with a rate. When I did that, the response was very different. It seemed to bounce better compared to just gradually applying the load. Are you with me? Now, there are almost all materials in real life which are rate dependent. Some are more rate dependent, some are less rate dependent. Okay. Supposing I conducted the same experiment and I got for 10%, I got something like this, let's say. This is more or less the same. So let's say this is epsilon dot is equal to 10% per second. It means that it is more or less the material is more or less rate dependent, independent. So we have rate dependent and rate independent materials. Okay. Yes. Somebody said not non-Newtonian fluid. Yes. Fluids as such, completely all fluids. What diagram do you draw? What is instead of stress? What do you use over here? I don't know if you're doing fluid mechanics now. What you do here is for a fluid. What you do here is you apply a shear, and here what you do is you apply as shear rate. So I'm going to call this as shear tau, and here you apply a rate of shear, and between rate of shear and tau, you plot a curve which tells me about how do I relate the stress with strain rate? Any idea? Any idea? Viscosity, right? So there it is between stress and stress and strain rate. Okay, because all fluids are rate dependent. Are you with me so far? Okay. Remember, I'm not plotting rate over here. I'm only plotting strain here and stress here, right? And if it is for different strain rate, if I get differently, it means rate dependent material. Most metals in room temperature are less rate dependent. Okay. More or less rate independent. Whereas materials which are made of plastic, uh, materials that are rubber like, all these materials do exhibit rate dependency. Same with our own body also, whether it is bone or tissue, skin tissue, etc., etc. They are all rate dependent. Okay. So any other point we need to make? Let's see. One last thing. Okay. Let's say I have a material that responds like this. Okay. So this is a ductile material. In another experiment, I do the same thing. I get a material that responds like this. Both are possible, right? Both are existent actually. What shall we call this material and what shall we call this material? Okay, right? This material, as I strain it, the stress level is increasing but slowly. Don't mistake me for using this word, but that's what they use. This is called strain hardening material. Okay. This material that you see over here is usually the response of rubber, tissue, etc., etc. You get something like that. Leather also has a very similar pattern like this. This is usually called, what shall we call this as? As I apply strain, it seems to have something that is changing. What is changing there? Yeah, this is also called strain softening. But usually what we use is strain hardening. Okay, hardening is, supposing I apply more load, it hardens. I'll tell you more about it when we come to plastic. But in this particular case, the slope seems to increase, right? If I plot the slope, slope is initially a constant and it starts to increase drastically. So this is called strain, strain, not softening, but strain, not softening, but what is changing? What is increasing? What is increasing as I strain it? What is increasing? Slope.
Straight.
What is slope? What is slope? Elastic is okay. It is stiffness. So what shall I call this kind of material as? Strain stiffening material. Fantastic. So this is strain stiffening materials. All right. Okay. Now let's just get a feel for numbers. Okay. So I'm just going to erase this. Feel for numbers now. We had some idea earlier, so we're going to progress further on that direction. Now, I'm going to name a material. I'm going to name a material, and you're going to tell me what is roughly the value of, let's say, there are two things, right? Strength. The other is stiffness. Okay. Shall we start? Let's on your keyboard on the chat box. Steel. I'm going to use strength as one of them. The other is stiffness. Okay. This is an MPA and this should be in GPA. Go ahead. 250, very good. 250 is pretty close. 250 MPA. Karthik, you're right. 250 MPA, roughly. It goes anywhere from 250 MPA to 700 MPA, depending on the way it is manufactured. Very good. How about stiffness? How about stiffness? Stiffness would be in GPA, right? 10 GPA. Vaishnavi says 10 GPA. Anybody else? Karthik says 400 GPA. Any other answer could be between or more or less. One more answer. One more answer. Go ahead. 25 GPA. 39. You're gradually increasing. We told yesterday, I think you've forgotten, 80, 200 GPA. It's around 200 GPA. Okay. Shall we try some other aluminum? Let's say aluminum. Aluminum. How about aluminum? 250. 250 is too much, no? Steel itself has 250, 100. Very good. So aluminum has anywhere between 70 and 100 MPa. Okay. And how about stiffness? Stiffness is usually, remember this all the time, between steel and aluminum, aluminum has a stiffness which is about one third of steel stiffness, about one third of steel stiffness. So roughly about 70 GPa is what you get. This also is applicable to copper. All right. Brass is a little bit better compared to aluminum or copper in its pure form. Aluminum, on the other hand, can be toughened very much. All right. So these numbers that I'm showing here are sort of a ballpark figure. Okay. Let me ask you this question. Okay. Surprise question. Bamboo. Bamboo. Don't look anywhere. Just feel. Get a feel for it. Go ahead. Bamboo. Bamboo. 50, 50 strength. I mean, we have strength here, stiffness here. We are talking about strength now. 50, 75, 75, 30, 100. No, your guess is not going correctly. 300. Fantastic. Karthik says 300. Sir, it is better than steel, is what you're saying. 600. Oh, too much, Nishan. So it's around 450. This is around 450. 450 MPa. Can you believe it? Bamboo in its longer direction. That is, if I have this in its transverse direction, it is very weak. You can just you can easily break it. You can just split it. But in the longitudinal direction, it's very strong. Okay. How about stiffness? Bamboo stiffness. This you will get fooled. 450 is the strength. What would be the stiffness? 30. So that's all. 150, 800. You'll be fooled. It's just 10 MPa. It's just 10 MPa. 10 GPa. Yeah, Siddharth, you were close, but it's just 10 GPa. Okay, how about our own hair, human hair in Tamil, just pulling the hair. We say in Tamil in a very similar way. What would be human hair? Any guess? 70. You won't believe it. This is better than aluminum. You have 150 MPa as the strength. Okay. And how about stiffness? Any idea? Stiffness? Harsha says 2.1. Pretty good. You people have started to guess better now. This is maybe a little bit better than skin. All right. So this is around point. Oh, sorry. This is around point 0.5. Okay. Now let's come to wood. How about wood? Wood. Fast. 3 more minutes. We'll complete this. 3 more minutes. This is around 30. Very good. Very good. 30 is a very good number. What else? How about stiffness? Stiffness. 10. Fantastic. Please don't look up anything and do this. Just get a picture in your mind. Okay. Okay. Rubber. How about rubber? Rubber. Natural rubber. Natural rubber. 2 MPa. Wow. 2 MPa, 10 MPa, 5 MPa. Yeah, roughly it's about 10 MPa. Okay. And Jeepa, stiffness. So remember now I'm saying MPa and Jeepa automatically, right? What would be the Jeepa of rubber? Very low, right? Very low. So it's less than the skin. It's about 0.1 MPa. If you vulcanize it, it becomes better. Okay. All right. All right. So we have done this, but let me ask you something more. Something more. The new inventions, right? Uh, gra- uh, carbon nanotube. Carbon nanotube. Carbon nanotube. Yes. 1,500. All right. 10,000. Wow. Mohammed says 10,000, right? When when they calculated, it is very difficult to do the experiment. So when they theoretically calculated, they found this to be roughly about 15,000 MPa. So remember this, I have to now start looking at, oh, what is the GPA of this, right? But MPa is around 15,000. And how about stiffness? Stiffness is also very high, around 1,000, right? So it's around anywhere between 800 and 1,000 is the calculation. Okay. Another material that is of late being talked about, which is graphene. How about graphene? Graphene, on the other hand, is one order more than this. It even goes to about 130,000, 130,000 MPa, right? How about stiffness? Stiffness is also one order higher than, almost one order higher than uh, uh, steel, right? So about not one order, about 4, 5 times more than that is what you see for carbon nanotube. Around twice at least is for graphene. So around 2,000 is what you see for graphene. Okay. What about diamond? What about diamond? I want you to look up all those. Lastly, there is one more material called carbine. Carbine. Okay. It's actually prepared by taking graphene and doing some processing in terms of wrapping it around the atom, etc., etc., so that you get this material, wonder material called carbine. And this carbine material is almost twice the strength of this. So we can go up to even 250,000 MPa. And the stiffness is also very, very high. One of the hardest materials that you can see, the hardest material here is around 4,000 odd GPa. Okay. What do we use for carbine for? Well, carbine is not in the production stage at all. It is in the lab. Even graphene, for that matter, is only in the lab stage. Most people do one thing, which is they use carbon fiber, just like glass fiber being used in composites. They use carbon fiber. Fiber has pretty good strength and stiffness. So we use that. Hardest is not diamond, by the way. Hardest is not diamond. Okay. So this is pretty high that we get as far as graphene and carbonyl are concerned. Why are why is it that steel does not have that kind of property? The answer has to do with what we did as the first experiment in this class. Hardest, not necessarily synthetic, Siddharth. Hardest is something that they figured out as, I don't remember, it's something called Neutra something. All right. They figured that this is what is existent in certain astronomical objects. Okay. Diamond, in fact, if you go down to the core of Earth, you get materials which are harder, it seems. Okay, but it's not possible for us to go that hard. So lab wise, they have come up with this kind of carbine or um, similar materials. Let's not go into details of those, but we get a ballpark figure here. Remember, steel that we are talking about here is bulk steel. I don't know if you understand what is bulk. Bulk here means that if I give you a bulk of, so where is that? Ah, I don't find what I used yesterday. Here. This is bulk steel. Okay. For this big steel, very big steel. Siddharth, you're going off the track now. This is bulk steel. The point I'm making is bulk means this is the length here or the dimension here is not at the nano level. Okay. If it is at the nano level, the properties will keep changing. I'll explain to you in a different class. Any questions so far? Any questions? And of course, you have Google, you can go and find out, but I want you to get a feel for the numbers. So let me ask you this question. When I say it is 250 MPa for steel, remember 1 dia or a little less than 1 dia or the area of the cross section being 1 millimeter square millimeter can stand a weight of how much roughly without getting yielded. What would be the weight it can carry quickly on the chat box? The cross section of the wire is 1 square, 25 kg, 250 newton. Yes, because it is 250 newton per square is MPa, which means that it can take about 25 kg without yielding. What do I mean by yielding? When I have something like this, and let's say I have now applied the load, when I remove it, it goes back. But at a particular point where it has crossed the elastic limit, it starts to yield. Okay. And this is not good for any structure, right? You don't want your pen to get deformed and therefore continue to use, right? So there is a point at which it starts to yield, meaning it starts to form permanent deformations. Okay, we call that as yielding. So this 250 that we're talking about here is the yield point of it. Okay, beyond which you will see permanent deformations. Okay, so in materials like steel or aluminum, we are talking about a point where yielding starts to occur. Okay, now let's do one thought design. Okay, let's say, so let me just use, I'm going to share screen. Are you able to see it? Are you able to see? This is what is this called? What is this called? What is this called? Gym rope. Very good. So this is a gym rope. Okay. So let me erase this. Okay. So story goes like this. Somebody heard, uh, who shall I call? Okay, Kinshuk. So Kinshuk is the designer. So the gym called Kinshuk and said, Kinshuk, we need to design this gym rope. Okay. All right. Kinshuk, tell me, what do you have to take care of? So I'm going to call this as design considerations. Quickly, let's see if we can. Number one, what question will you ask? You can go into voice mode also and state it. Go ahead. If not Kinshuk, anybody else also is okay. Let's say all of you are together, or the designers, and you need to design this gym rope. What questions will you ask? Go ahead. Why silence here? What questions will you ask? What is the first thing that I have to ask is, okay, this is used for climbing, correct? How much weight? Fantastic. Mohammed is right. How much weight? Right? How much weight should I consider? What will weight give me? The weight will give me what will weight give me? The weight will give me what? The stress that the rope is carrying, correct? All right. What else? One of them is saying uh, grip, grip that it provides. Okay. What else? Strength of the rope. Very good. Strength of the rope. So support strength, I'll say. Okay. Support strength. What else? Weight to be carried, support strength. What else will I ask? Length of the rope, dimensions are given to you, let us say. This is a gym rope, let's say 20 feet. Okay, that doesn't matter, Kinshuk. Anybody else can, if you want to do it on chat mode is also fine. Support strength. What else? What else are the considerations that you look at quickly? How much it might elongate? Very good. So elongation of the rope. Very good. What else? Rope cross section. Rope cross section, you cannot ask the client. The client is saying, okay, you need to come up with the rope, right? And you can ask the client about any question, right? Elasticity, again, your own, the question that you have to ask as a designer for yourself. What would you ask the client? Anything else? Rope should have high tensile. Yes, we'll come to that. What else? What other question would you want to ask the gym owner? Cost of the material. Very good. What else? Cost, budget, same thing, or cost or budget. Somebody says, how much will it last? Fantastic. Lifetime. You would say a lifetime warranty I need. Okay. Or tell me how long do you want this rope to be surviving? Friction due to that client cannot tell you about friction. You need to figure out. The thickness of the rope, you need to figure out and tell. We'll just put this as thickness of the rope, but come back to this very quickly. Thickness of the rope. Okay. Just 5 more minutes. Let's ask each question. How much weight? How much weight will I consider now? How much weight? 100 kg. Why 100 kg, Mohammed? Why should it be 100 kg? Why can't it be 120 kg? Why should it be 80 kg? Why should it be 200 kg? Give me on an average of what? On an average of what? Siddharth, tell me a scenario. Weight of the person. Very good. Weight of the person. Now you are a designer, right? You will ask what would be the, will you ask average weight of the human or maximum weight possible? Upper limit. Very good. It is the upper limit. Now, what is the guarantee that you will have only one person climbing? Right? There's a possibility that two people may be climbing at the same time. Right? So I need to now look at, okay, let me just design it so that not more than two people will climb at any point of time. So I'll be giving a specification. Okay, if you are using it, you should use it with these things. Monkeys in the gym, whatever. You're now going into a lot of imagination. But the point is, 2 kgs, two people, let's say very heavy people, let's say about 120, 130 kgs, two of them, 250 kgs is the weight for which I want to design. Very good. Okay. Grip that it has to provide depends on how it is made. We'll come back to that later. Support strength, let us assume that we have the ceiling that can take care of this. This is a separate design that needs to be done. Elongation of the rope. Let's ask that question. Elongation of the rope. What could be the elongation of the rope? Let us say the height from which it is hanging to start with, let's say is about let's say about 20 feet, which is about 6 meters. Okay, 5 meters, 5 to 6 meters. All right. So I'm looking at 6 meters. How do I now decide what would be the value that is allowable, tolerable? That depends on the human psychology, right? If I pull and it just comes down, just like bungee rope, then I would hesitate going up. Correct. So roughly, I'll be okay with if it is about maximum of 1 centimeter or 10 mm. So anywhere between 5 mm or to 10 mm, I'll allow it. So this is allowable. This is design load. Okay. Okay. I have elongation. I have design load. What is missing now? I have elongation. I have design load. What is missing? Lifetime. Okay. Lifetime. We'll come to lifetime. Lifetime has to do with what? What should I consider for lifetime? Fatigue. Very good. Durability has to do with fatigue. So how many load cycles, loading and unloading, loading, how many times will it be able to stand? That's another question. So given the first preliminary design, I will start with the elongation and the load, and I now have to decide something. What is that decision I have to make as a designer? The first decision that I have to make, grip friction comes much later. I can have a coating that thing. What is the stiffness is one of the points. What is the strength? Before asking all those questions, okay, now let's look at that. 250 kgs, which is 2500, 2500 Newton per mm square. 5 mm elongation, allowable for, let's say, 5 meters, right? Which is 5000 mm. So 5 mm by 5000, I get 0.001, right, as the percentage of strain. Okay, so now I have a fair picture of what would be the stress that is allowable, what would be the strain that is allowable. I have stress that is allowable, strain that is available. I will be looking at, okay, what material shall I use? Here comes the important question. I'll stop with that. What would be the important question that I will ask? How do I choose the material? Just, uh, of course, stiffness and strength are things that determine the material. There'll be a lot of materials. Cost is one of them, correct? I'm missing something. Has to do with grip. Let us say I'm a sort of freaky guy, freaky person. I'll go for, let's say, carbine cable. Is that okay? carbine cable. Why not? Why not? Tell me why not? Why can't I use for carbine cable? It is expensive. Let's say a gym owner says, I can afford, sir, easily available. Let us say it is available. Even then, is it okay? What is the consideration I'm missing out? Not elastic, not harmful. It doesn't feel right. Flexibility, not yet, sir. Yeah, Vaishnavi, if it is smooth, I can roughen the surface, etc., etc. That's not a problem. Too stiff, so what if it is too stiff? This is only allowable. If it is lesser, it's merrier. Not possible to get into rope shape. Why should I be looking at rope shape? It is just a cable, right? Should have a large cross section. Fantastic, Bindu. But what is it? Bindu, Bindu is saying it should have large cross section. Why should it have large cross section? Fantastic response. Why? What do you mean by large cross section? With that, I'll stop. Ah, fantastic. I should be able to hold, right? If it is very thin, if I have something like this, if it is very thin like this, do you think I can hold enough and climb? I need to have enough surface area for the finger to hold and go up. And therefore, I also have to consider a cross section that is comfortable with my hand. So probably my hand closes with a particular diameter. It may be about, let's say, an inch and a half. Okay, there may be a child also using it, which may be about less than an inch. There's a huge man who is using it, which may be probably, I can go like this, probably 2 inch dia. So I need to have that range and look at, okay, this is the cross section I have to choose. The moment I use the cross section, then I now zero in on certain materials that I can use. Okay, and then I'll go about choosing the material. So choosing the material is the first step that you do in terms of design, and then go about looking at all the other aspects of the rope. Is this clear to you? Okay. And I also have to look at, okay, having chosen the material, what would be its fatigue limits, etc., etc. Okay. I'm running out of time. We'll continue in the next class. Tomorrow is a working day. So tomorrow we will be meeting Thursday's timetable. Okay. Oh no, yeah, yes, correct. What to do? I also thought it's a holiday, but it is not a holiday. So we'll meet. One last thing, if you people want to have a discussion session on the first assignment, I'll post when I'm available on Friday. You can come and have a discussion. Okay, most probably it will be later in the afternoon, around 6 o'clock or 7 o'clock. I may have a window of 7 to 9 p.m. on Friday. I'll let you know tomorrow. Okay, thank you. Have a good day. Enjoy.